Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. Comets have long fascinated humanity, their sudden appearances across the night sky inspiring awe, fear, and curiosity. For centuries, they were seen as omens, mysterious harbingers of change that defied human understanding. Today, with the eyes of science and technology, comets are no longer just symbols of the unknown. They are tangible relics of the early solar system, frozen time capsules carrying secrets from the era when our sun and planets were first forming. These cosmic snowballs, composed of ice, dust, and a mixture of frozen gases, drift through the cold reaches of deep space, only occasionally venturing close enough to the sun to reveal their spectacular displays. A comet's journey is one of extremes. Born in the outermost regions of the solar system, often in the Kuiper Belt, or even farther in the distant Oort cloud, comets are formed from the primordial materials that built the planets. In these icy realms, temperatures are so low that volatile substances such as water, carbon dioxide, methane, and ammonia freeze solid. Within these frozen bodies, microscopic dust grains are embedded, creating a complex mixture that has remained mostly unchanged for over 4 billion years. This makes comets unique windows into the conditions of the early solar system, far more pristine than the planets, which have undergone continuous reshaping by geological and atmospheric processes. The anatomy of a comet is simple yet fascinating. At its heart lies the nucleus, a solid, often irregularly shaped core that ranges in size from a few hundred meters to tens of kilometers across. The nucleus is the foundation, a compact mixture of ice and dust, sometimes described as a dirty snowball, because of the way rocky particles are embedded within icy material. Surrounding the nucleus is the coma, a cloud of gas and dust that forms when the comet approaches the sun. The coma can expand to thousands of kilometers in diameter, glowing brightly as sunlight vaporizes the ices, releasing gases and carrying dust particles away from the nucleus. From this cloud, the iconic cometary tail extends, often stretching millions of kilometers, pointing away from the sun due to the pressure of solar radiation and the solar wind. Interestingly, a comet usually has two tails, a dust tail, which arcs gently along the comet's orbit, and an ion tail, a straight bluish stream formed by charged particles interacting with the sun's magnetic field. Despite their delicate beauty, comets are powerful agents of change in the solar system. Their impacts on planets and moons have shaped surfaces, delivered water, and perhaps even contributed organic molecules crucial to the origin of life on Earth. Ancient collisions with comets may have brought large quantities of ice to the early Earth, adding to the primordial oceans. Some theories suggest that the building blocks of life, including complex organic molecules, could have been carried by comets, seeding young planets with the raw ingredients necessary for life to begin. Even today, as comets streak past planets, they continue to influence the solar system's dynamics, nudged by gravity into new orbits, sometimes becoming long-term visitors to the inner solar system, or eventually being ejected into interstellar space. The behavior of comets is as unpredictable as their appearances. Some comets visit the inner solar system at regular intervals, like Halley's Comet, which reappears roughly every 76 years, a celestial clockwork that has fascinated humans for generations. Others follow more chaotic paths, making a single, rare pass close to the sun before disappearing back into the distant reaches of space. As a comet nears the sun, the increase in heat triggers sublimation, the process by which solid ice turns directly into gas. This creates spectacular displays that can light up the sky, sometimes becoming visible even in daylight. Ancient astronomers were both terrified and mesmerized by these luminous visitors, interpreting them as omens, warnings, or messages from the gods, while modern science sees them as invaluable natural laboratories. Exploration of comets has evolved from mere observation to direct encounter. Space missions have transformed our understanding by allowing scientists to study comets up close. Missions like ESA's Rosetta, which followed Comet 67P/Churyumov-Gerasimenko for over 2 years, provided unprecedented insights into a comet's structure, composition, and behavior. The mission even deployed a lander, Philae, which touched down on the nucleus, revealing surface features, chemical compositions, and the complex interplay of ice and dust. These missions have shown that comets are more diverse than previously imagined. Some possess jagged cliffs, deep pits, and rugged terrains, while others are smoother, covered in a thin layer of dust. Their surfaces change over time as jets of gas erupt, reshaping their landscapes and releasing material into space. Observations from both Earth and spacecraft have revealed that comets carry an astonishing variety of chemical compounds. Water is abundant, but alongside it are organic molecules such as formaldehyde, methane, and even amino acids, hinting at the rich chemistry that may have contributed to life on Earth. The isotopic composition of cometary water is a subject of intense study as it helps scientists understand whether comets were a primary source of Earth's oceans. Some comets, like those from the Jupiter family, show compositions that closely resemble terrestrial water, supporting the idea that our planet's early environment may have been influenced by cometary deliveries. The study of cometary chemistry not only informs us about the origin of the solar system, but also helps guide the search for life elsewhere, providing clues about where similar processes might occur around other stars. The orbits of comets are as varied as their compositions. Some follow short-period orbits, taking only a few years to circle the sun, while others embark on journeys lasting thousands or even millions of years. Long-period comets, originating from the distant Oort cloud, can enter the inner solar system from any direction, often moving on nearly parabolic trajectories. Their visits are rare and unpredictable, and each appearance is a unique opportunity for study. Short-period comets, influenced by the gravity of the giant planets, often return along predictable paths, providing astronomers with a chance to observe them over decades. The interplay of gravitational forces, solar radiation, and sublimation creates a dynamic, ever-changing ballet in which comets dance through the solar system, their tails whispering stories of ancient origins. Throughout history, comets have been more than just celestial phenomena. They have influenced human culture and thought. From the ancient chronicles of Mesopotamia to the detailed astronomical records of China and medieval Europe, comets were noted for their brilliance and their timing, often coinciding with significant events. Artists and writers captured their beauty and mystery, weaving comets into myths, literature, and art. The recurring appearance of Halley's Comet inspired folklore and scientific inquiry alike, demonstrating the human desire to understand and predict the cosmos. Today, while fear has been replaced with curiosity, the fascination remains. Observing a comet streak across the sky evokes a profound sense of connection to the vastness of the universe and the fragile passage of time. Modern technology has opened new windows into cometary science, allowing astronomers to study them in multiple wavelengths. Telescopes sensitive to infrared light reveal the heat of dust grains and sublimating ice, while ultraviolet and X-ray observations uncover the interaction of cometary gases with solar radiation. Radar studies can map a comet's nucleus and reveal its rotation, shape, and surface structures. The combination of these techniques has transformed our understanding, showing that comets are not just passive balls of ice, but active, evolving objects, each with its own personality and history. They are laboratories in motion, carrying within them the story of the solar system's infancy, the primordial soup of material that ultimately led to planets, moons, and the conditions necessary for life. The human drive to explore comets is more than academic. Understanding their behavior is crucial for planetary defense. While most comets pass harmlessly by, a direct collision with a large comet could have catastrophic consequences for Earth. Studying their orbits, compositions, and physical properties helps scientists model potential impacts and develop strategies to mitigate risks. Missions designed to observe, rendezvous, or even redirect cometary bodies are not merely exercises in curiosity. They are practical steps towards safeguarding our planet while advancing knowledge. The same techniques that help us understand comets also prepare humanity to navigate a solar system where cosmic collisions are a real, if infrequent, threat. Comets continue to inspire innovation and ambition in space exploration. Proposals for future missions include sample return missions, allowing scientists to bring pristine cometary material back to Earth for detailed laboratory study. Others envision long-term orbiters that could monitor comets over years, providing insights into their evolution and activity cycles. Beyond scientific curiosity, there is even speculation about utilizing comets as resources in space. Their water ice could be converted to fuel for spacecraft, and their organic compounds could support life in off-world colonies. In this sense, comets are not only relics of the past, but potential contributors to humanity's future in space, bridging the ancient and the futuristic in a single celestial object. The fleeting brilliance of a comet reminds us of the transient nature of celestial events. Each approach to the sun is a temporary spectacle, a luminous performance in a dark, vast theater. While the nucleus may endure for billions of years, the bright coma and tail are ephemeral, shaped by the forces of solar heat and radiation. Observers on Earth witness only a brief chapter of the comet's journey, yet in that short time they glimpse a fragment of the universe's history. Comets connect the present to the distant past, their frozen materials carrying messages from a time before planets coalesced, before life emerged, and before the solar system took on the forms we recognize today. The study of comets also intersects with the broader understanding of planetary systems beyond our own. Astronomers have discovered exocomets orbiting distant stars, detected by the subtle dimming of starlight as they transit or through the absorption lines created by their evaporating gases. These observations suggest that comet-like bodies are common in planetary systems throughout the galaxy, carrying the same potential for delivering water, organic compounds, and shaping planetary environments. By studying comets in our solar system, we gain insights into the processes shaping other worlds, understanding the universality of certain cosmic mechanisms, and the diversity of outcomes in planetary evolution. Ultimately, comets are more than ice and dust. They are storytellers, archivists, and catalysts. They narrate the origins of the solar system, preserve chemical signatures from its infancy, and interact with planets in ways that shape environments and perhaps life itself. They challenge our imagination and provoke scientific inquiry, compelling humans to observe, study, and reach out. Their paths are unpredictable, their appearances sporadic, yet their significance is enduring. In every luminous streak across the night sky, in every icy nucleus revealed by a spacecraft, comets remind us of the vast, interconnected cosmos, where even the smallest, most fragile object can carry the weight of history, the seeds of life, and the promise of discovery. The cosmic snowballs that wander through deep space are humble, yet extraordinary. They remind us that the universe is both ancient and dynamic, filled with objects that have witnessed the birth of planets and stars, and will continue their silent journeys long after humanity is gone. They beckon us to explore, to understand, and to marvel. Comets are the messengers of the deep, the icy wanderers whose brilliance lights the darkness, whose composition preserves the earliest stories of our cosmic neighborhood, and whose presence continually invites humanity to reach upward, gaze outward, and embrace the mysteries of the universe. Comets are remarkably diverse, and scientists categorize them based on their orbital periods and origins. Short-period comets, often called Jupiter family comets, complete an orbit around the Sun in less than 200 years. Their paths are heavily influenced by the giant planets, particularly Jupiter, whose immense gravity can nudge them into new trajectories or even eject them from the solar system entirely. Long-period comets, by contrast, can take thousands or even millions of years to return, originating from the distant Oort cloud, a vast spherical shell surrounding the solar system. These long-period comets often arrive from directions far removed from the plane of the planets, their journeys through interstellar space shaping trajectories that seem random from an Earthbound perspective. This classification not only helps astronomers predict their appearances, but also provides insights into the dynamics and structure of the outer solar system. The visual spectacle of a comet is not merely a product of chance. It is a physical consequence of the interactions between ice, dust, sunlight, and solar wind. As a comet nears the sun, sublimation releases gas, which in turn drags dust particles away from the nucleus. The solar wind, a stream of charged particles emitted by the sun, interacts with these gases to form the ion tail, a glowing, often blue stream pointing directly away from the sun, regardless of the comet's direction of travel. The dust tail, more gently curved and yellowish in hue, reflects sunlight and can stretch across the sky in sweeping arcs. This dual-tail structure, first understood in the 20th century, is one of the most beautiful manifestations of fundamental physics in the cosmos, showing how microscopic particles and electromagnetic forces can create macroscopic phenomena visible from millions of kilometers away. While the classical view of comets as icy wanderers has remained consistent, modern observations have revealed unexpected complexity. Some comets display a remarkable heterogeneity in surface composition, with regions dominated by ice, others covered in a thick layer of dark dust. Jets of gas and dust erupt from localized areas, forming plumes that can alter the comet's rotation and gradually reshape its surface. Thermal stress from repeated passages near the sun can cause cracks, cliffs, and even splitting events, where the nucleus fractures into multiple pieces. These dynamic processes reveal that comets are not inert relics, but living, evolving bodies, constantly reshaped by the forces they encounter. Observing these changes in real time provides astronomers with a natural laboratory for studying physical and chemical processes under extreme conditions. The history of comet observation is a rich tapestry blending science, culture, and mythology. Ancient civilizations meticulously recorded the appearances of comets, linking them to events on Earth, or interpreting them as divine messages. Chinese astronomers created detailed star charts that included comets, noting their positions, lengths, and brightnesses. In Europe, medieval chroniclers often associated comets with plagues, wars, or the deaths of rulers. These historical records, although interpreted through the lens of superstition, are invaluable to modern science, providing evidence of cometary behavior centuries before telescopic observations were possible. Comparing historical accounts with modern data allows astronomers to track cometary orbits over centuries, revealing patterns and enabling predictions about future appearances. One of the most famous comets in human history, Halley's Comet, exemplifies the enduring fascination with these celestial wanderers. Named after Edmund Halley, who first calculated its periodicity, this short-period comet has been observed and recorded for more than 2 millennia. Its appearances have coincided with pivotal moments in human history, from the Bayeux Tapestry, which depicts it during the Norman conquest of England, to scientific observations in the modern era. Halley's Comet demonstrates the interplay of predictability and wonder, showing that even an object governed by gravitational laws can inspire generations of curiosity, creativity, and awe. Scientific exploration of comets has moved beyond observation to direct study through spacecraft missions. The European Space Agency's Rosetta mission, which rendezvoused with Comet 67P/Churyumov-Gerasimenko, provided unprecedented insight into a comet's nucleus, surface morphology, and activity. Rosetta's observations revealed towering cliffs, deep pits, and regions of smooth terrain, challenging prior assumptions about cometary surfaces. The Philae lander, despite its bumpy landing, transmitted data revealing organic compounds, water ice, and complex surface chemistry. Similarly, NASA's Stardust mission captured dust from Comet Wild 2 and returned it to Earth, allowing laboratory analysis of cometary materials and confirming the presence of minerals that formed under high temperatures, hinting at the mixing of materials within the early solar system. These missions highlight the technological ingenuity required to explore small, fragile objects millions of kilometers away and demonstrate how human curiosity drives us to seek knowledge in the most extreme environments. Beyond science, comets have practical significance for humanity. Understanding their orbits and compositions is critical for planetary defense. While the risk of a large comet impact is low, the consequences could be catastrophic, comparable to or exceeding the asteroid impact that contributed to the extinction of the dinosaurs. Monitoring comets and modeling their trajectories allow scientists to anticipate potential threats and develop mitigation strategies. Techniques under consideration include deflecting or disrupting an approaching comet, using gravity tractors, kinetic impactors, or even focused solar energy. Preparing for such scenarios requires a detailed understanding of cometary structure, density, and composition, underscoring the intersection of curiosity-driven research and pragmatic planning. Comets also hold promise as resources in future space exploration. Their abundant water ice could be converted into liquid water, oxygen, and hydrogen fuel for spacecraft, potentially serving as refueling stations in deep space. Organic molecules carried by comets might provide raw materials for life support in off-world colonies. The study of cometary resources is part of the broader field of in-situ resource utilization, where materials found on celestial bodies are used to support human activity in space. This vision transforms comets from remote scientific curiosities into tangible assets for humanity's expansion into the solar system, linking exploration, science, and survival in a profound way. Notable comets continue to surprise and inspire. Comet Hale-Bopp, visible to the naked eye for months in 1997, captivated millions with its brilliance and extensive tail, becoming one of the most observed comets of modern times. Its extended visibility allowed astronomers to study its behavior in detail, revealing jets of almond dust, complex coma structures, and interactions with the solar wind. Comet Shoemaker-Levy 9, which famously collided with Jupiter in 1994, provided a dramatic demonstration of the destructive potential of comets and the dynamic nature of the solar system. The impacts created massive fireballs, scarred Jupiter's atmosphere, and offered a unique opportunity to observe the effects of a cometary collision in real time, underscoring the relevance of comets both as subjects of study and as actors in cosmic events. Comets are also important in the broader context of planetary systems. Observations of exocomets orbiting distant stars suggest that comet-like bodies are common throughout the galaxy, carrying water and organic compounds to young planets. These findings imply that the processes that shaped our solar system are not unique, and that comets could play similar roles in delivering the building blocks of life elsewhere. The study of comets, therefore, is not just a window into our past, but a guide to understanding planetary formation and the potential for life in the cosmos. Each comet observed, whether near or far, provides clues to universal processes that have shaped planets and stars for billions of years. The chemistry of comets is an area of ongoing fascination. Within their ices and dust, comets preserve molecules that are the precursors to life. Amino acids, nucleobases, and complex organic molecules have all been detected, suggesting that comets may have played a role in seeding Earth with the ingredients necessary for life. The isotopic ratios of hydrogen and oxygen in cometary water provide clues about the origins of Earth's oceans, helping to resolve long-standing questions about how our planet became habitable. Laboratory studies of cometary samples, combined with remote sensing from spacecraft, continue to reveal an intricate chemical narrative, showing that even the simplest appearing icy wanderers are chemically rich and diverse. The dynamic evolution of comets is a testament to the forces at play in the solar system. Repeated passes near the sun gradually erode the nucleus, sublimating ice and releasing dust, forming spectacular tails. Over time, some comets break apart, leaving trails of debris that can generate meteor showers when Earth passes through them. This cycle of creation and destruction illustrates the interconnectedness of celestial bodies. Comets contribute to planetary atmospheres, seed meteoroid streams, and even affect planetary surfaces. Observing these processes in real time allows scientists to witness evolution on a cosmic scale, a rare glimpse into the life cycle of objects born in the solar system's earliest epochs. The allure of comets lies not only in their science, but in their ability to evoke wonder. Standing under a dark sky, watching a comet streak across the stars, humans feel a connection to the cosmos, a sense of participation in a universe that is vast, ancient, and dynamic. Comets remind us of our place in the solar system, bridging the gap between distant history and immediate experience. They inspire art, literature, and imagination, as well as rigorous scientific inquiry. In their fleeting brilliance, comets carry the dual role of teachers and storytellers, sharing knowledge about the cosmos while stirring the human spirit. Comets, as cosmic snowballs from deep space, encapsulate the history, dynamics, and chemistry of the solar system. From their icy origins in the Kuiper Belt and Oort cloud to their spectacular displays near the sun, they traverse extremes of distance, temperature, and radiation. They carry the story of planetary formation, preserve the building blocks of life, and continue to shape our understanding of the universe. They are agents of change and preservation, destruction and creation, familiar yet unpredictable, simple yet complex. Each comet observed is an opportunity to learn, to marvel, and to reflect on the intricate, interconnected processes that govern the cosmos. Comets have inspired not only scientists but also artists, writers, and philosophers throughout history. Their sudden appearance in the sky, often bright and dramatic, has made them symbols of change, mystery, and the unknown. In medieval Europe, comets were frequently depicted in illuminated manuscripts, sometimes accompanied by imagery of chaos or divine judgment. During the Renaissance, artists incorporated comets into their works to emphasize cosmic significance or historical events, blending observation with imagination. Writers and poets have long used comets as metaphors for fleeting beauty, destiny, and the forces beyond human control. Even in modern times, comets appear in science fiction and popular culture, where they represent both opportunity and danger, serving as portals to explore humanity's relationship with the wider universe. The observation of comets has evolved dramatically over centuries. Early astronomers relied on naked eye sightings, recording positions, brightness, and movement with painstaking care. The invention of the telescope opened new possibilities, allowing detailed study of cometary tails and structures. Today, a combination of ground-based telescopes, space observatories, and robotic spacecraft enables unprecedented precision. Spectroscopy allows astronomers to identify the chemical composition of comets, measuring the presence of water, carbon compounds, and exotic ices. Infrared telescopes detect heat from dust and sublimating ices, while ultraviolet and X-ray instruments reveal the interaction of cometary gases with solar radiation. Radar studies map the shape and rotation of nuclei, providing insights into internal structure. Together, these tools create a multi-dimensional understanding, transforming comets from distant points of light into well-characterized celestial bodies. Historical comets offer rich lessons for modern science. Comet Halley's appearances have been recorded since at least 240 BCE, providing data on orbital stability and periodicity over millennia. Comet Hale-Bopp in 1997 offered an extraordinary opportunity for both professional and amateur astronomers. Its brightness and long visibility, allowing detailed monitoring of coma evolution, tail formation, and outgassing events. Comet Shoemaker Levy 9's collision with Jupiter in 1994 demonstrated the dynamic and sometimes violent interactions comets can have with planets, highlighting the role of gravitational perturbations and the potential for cosmic impacts. Each historical comet, therefore, serves as both a scientific case study and a cultural milestone, bridging human experience with the mechanics of the solar system. Future exploration of comets promises to deepen our understanding even further. Planned missions aim to return cometary samples to Earth, providing pristine material for laboratory analysis, revealing chemical structures with accuracy impossible to achieve remotely. Orbiters designed to follow a comet over months or years will allow scientists to observe seasonal changes, sublimation cycles, and surface evolution. Concepts for crewed missions, though ambitious, envision astronauts studying comets up close, deploying instruments, and possibly utilizing cometary resources. Such missions highlight the multifaceted value of comets: scientific, practical, and inspirational. They are laboratories for fundamental research, potential suppliers of water and fuel in space, and enduring symbols of humanity's curiosity and drive to explore. Meteor showers, linked to cometary debris, provide another example of the indirect influence of comets. When Earth passes through trails of dust left by comets, the particles enter our atmosphere at high speed, burning up and creating brilliant streaks of light. Annual events such as the Perseids, originating from Comet Swift-Tuttle, or the Leonids, associated with Comet Tempel-Tuttle, transform ordinary nights into celestial spectacles. These showers demonstrate the interconnectedness of cosmic phenomena. Comets shape not only their immediate surroundings, but also the experiences of planets far away. Observing meteor showers provides a tangible link to cometary material and emphasizes the dynamic, ever-changing nature of the solar system. Comets also challenge our understanding of physics under extreme conditions. The sublimation of ice, the formation of jets, and the acceleration of dust particles reveal complex interactions between thermal, gravitational, and electromagnetic forces. Cometary outbursts, sometimes dramatic and unpredictable, illustrate the fragility and activity of these icy bodies. Rotational dynamics are influenced by asymmetric outgassing, which can gradually alter a comet's spin or even lead to fragmentation. These processes provide natural laboratories for studying mechanics, thermodynamics, and chemistry in environments impossible to replicate on Earth, enriching our understanding of fundamental physical principles. In the broader context of planetary science, comets are integral to the story of solar system formation. Their chemical compositions reflect the conditions of the early protoplanetary disk, preserving clues about temperature gradients, radiation environments, and the mixing of material. By comparing cometary data with that of asteroids, planets, and moons, scientists reconstruct the evolutionary pathways that led to the current arrangement of the solar system. Comets reveal the distribution of volatiles, the movement of material between regions, and the processes that allowed planets to accumulate water and organic compounds. In essence, each comet is a chapter in the narrative of cosmic evolution, offering insight into the forces and processes that shaped our celestial neighborhood. Comets are not static relics. They interact with other celestial bodies in the interstellar environment. Collisions with planets or moons can leave craters, deposit volatile materials, and trigger geological or atmospheric changes. Even gravitational interactions with the sun and planets can modify cometary orbits, sending them on new trajectories or expelling them into interstellar space. Some comets may even originate outside our solar system, entering on hyperbolic paths as interstellar visitors, offering glimpses into material formed around distant stars. The discovery of such objects, like Oumuamua and Comet Borisov, expands our understanding of comets beyond the solar system, illustrating the universality of these icy wanderers and the continuity of processes throughout the galaxy. The fascination with comets also lies in their symbolic resonance. They embody transience, change, and the interplay between permanence and impermanence. The icy nucleus, billions of years old, travels immense distances and survives cosmic extremes, while the brilliant tail appears only briefly, an ephemeral expression of cosmic forces. This duality captures human imagination, a tangible connection to ancient history, yet a reminder of the fleeting nature of observable phenomena. Observing comets encourages reflection on time, scale, and the universe's capacity for both stability and transformation, reinforcing the profound impact these celestial objects have on both science and culture. As humanity continues to explore space, comets offer opportunities that extend beyond scientific research. They can serve as stepping stones for deep space exploration, sources of water and fuel, and laboratories for testing technologies in microgravity and extreme environments. The study of cometary materials may guide the development of life support systems, fuel production methods, and other technologies essential for long-duration missions. By combining scientific curiosity with practical applications, comets bridge the gap between understanding the past and preparing for the future, demonstrating their enduring relevance to human endeavors in space. In conclusion, comets are remarkable in both their simplicity and complexity. They are cosmic snowballs from deep space, carrying the secrets of the solar system's formation, the building blocks of life, and the forces that govern planetary dynamics. Their fleeting brilliance inspires wonder, their chemical richness offers insight, and their journeys through space connect the present to the distant past. From ancient myths to modern space missions, from meteor showers to interstellar visitors, comets shape both our understanding of the universe and our cultural imagination. They are silent storytellers of time and space, icy messengers that remind humanity of the vastness of the cosmos, the fragility of existence, and the enduring drive to explore, understand, and marvel at the mysteries of the universe.